This meeting is being recorded.
In the last video, in sections 1.8 and 1.9, we saw valence bond theory and molecular orbital theory, and we saw an interaction of atomic orbitals to form bonds, but we didn't review or comment on orbital hybridization. So in this video, we're going to look at this important aspect of organic chemistry, these hybridized atomic orbitals. And we're going to use carbon here as an example, since, carbon is what defines organic chemistry, carbon, molecular compounds that have carbon. So we see here the ground state electron configuration. So that's what we see over here. And this is showing us an energy diagram with increasing energy as we go up. So the 1s orbital is the lowest, then the 2s, then the highest energy is the 2p orbital. And we see all of the valence electrons and all the inner electrons as well, the core electrons down there. So let's take a look what happens when we excite carbon, right? So some form of energy causes this excitation. So this electron here has moved from the 2s orbital up to the 2p orbital. So we've created this excitation from the ground state. So this still does not explain, if we look at methane here, the simplest hydrocarbon that we'll be introduced to this semester, right, CH4. So we have a carbon surrounded by 4 hydrogen atoms. So all of these bonds, these 4 bonds between the carbon and hydrogen are the same. So they're all the same. So someone realized, early on in this analysis of the bonds of this methane molecule that they all have to have the same energy then associated with them if they're all appearing the same on analysis. So what actually happens is the 2s orbital and all 3 of the 2p orbitals interact in a way that there are 4 equal bonds made. In this image here, we know that we cannot make 4 equivalent bonds. So let's move to the next slide here, and let's see what actually happens. So that 2s electron and the 3 2p electrons are housed now in what are called 4 degenerate sp3 orbitals. So we see 1, 2, 3, 4. Degenerate means equal energy atomic orbitals, and now the overlap of these hybridized orbitals, so say this is from our carbon atom, this is my sp3 hybridized orbital, would overlap with the hydrogens, right, s orbital here, and we would see this bond that forms would be equal if we use these 4 degenerate hybridized sp3 atomic orbitals. So what this looks like here is the P character over here and some of the S character over here would form this sp hybridized orbital. So this is how an hybridized orbital appears, and this one specifically is an sp3 hybridized orbital of the carbon atom. And it's good to note that it has 25% S character and 75% P character because the original electrons, 3 out of 4 were from the P orbital and 1 out of 4 was from the S orbital. So that's where we get the numbers, right? 1 out of 4, right? 1/4 equals 25%, 3/4 equals 75%, and this will be important when we look at things like acidity and different character of different types of hybridized bonds that form. So keep your attention to that later on in the semester. So this next slide here shows this overlap that occurs much better than the drawing that I just did with the hybridized orbital and then the s orbital overlap. So you can see the 1 electron from the hydrogen here, the 1 electron in this bond here, and then the 2 are overlapping over here. And they even gave us that that tetrahedron inside to remind you of the molecular geometry that results with this type of sp3 overlap with the hydrogen's s orbital. We get a tetrahedral molecular geometry. So that will be important again when we get to reaction mechanisms, the molecular geometry, whether it's tetrahedral or things like trigonal planar. So if you don't recall what I just said there, tetrahedral and trigonal planar, definitely review those concepts. Because now let's look at ethylene, and we can see this planar type of geometry and these different bond angles in the molecule here. So we see this HC bond angle is about 121, and then over here the HH angle is about 118 degrees. So it's not so much important to memorize the angles and their degrees, but just know whether or not the molecular geometry that results is trigonal planar or tetrahedral. So again, we see that in this ethene, aka ethylene, was the common nomenclature, but the same thing, the same compound we'll reference here. So now we have an unhybridized, if you recall that term, unhybridized, UNH, unhybridized. Okay, that looks good. So this unhybridized p orbital is not involved in forming hybridized orbitals. So we only need 3 total. One for the double bond, that sigma bond, and then 2 sigma bonds for the hydrogen atoms. So we have a total, right? 1, 2, 3 sp2 hybridized orbitals, degenerate, right? All the same energy are now created. And those would be all the sigma bonds, right, that form would be from these 3 hybridized orbitals. So you can see another angle of this illustrated here where we have this p orbital, right? The red lobe is the upper portion that has the electron in it at that time, and then down here we have the blue lobe. So this p orbital is not involved in the sp2 hybridized orbital creation because we only need 1 s and then 2 of the p to give us a total of 3 sp2 hybridized orbitals. One other thing to note is the percentage of S character versus P character. So we only have a total of 3 orbitals involved in our hybridization. So 1 out of 3, right, gives us about 33%. And then the 2 P orbitals out of 3 give us that 67% P character. So again, we'll talk about why that is important when we get to reactivity and acids and bases and things like that. So now we have a couple more slides. So I'll move a little quicker now because I mentioned that this is the sigma bond from the hybridized orbital that's involved in this overlap here. And then, right, this would be our sigma bond. And then our pi bond involved in the double bond is from the 2 p orbitals that are not involved in the hybridization. So that extra p orbital, that overlap is what forms our pi bond there. So that overlap of p orbitals is the pi bond. So that's where the second of the double bond comes from. So you can recall that the side-to-side overlap is what causes our pi bonds to form. And it's good to note that they are weaker than sigma bonds. So when we get to, again, enthalpy changes and breaking bonds and forming bonds and calculations like that, we'll reference that again. And this here shows us our pi bonding molecular orbital and our pi antibonding molecular orbital. So last section we looked at our sigma bonding and antibonding molecular orbitals. This is the same concept. We're just using 2p atomic orbitals here to form our 2 pi bonding and antibonding molecular orbitals. Remember that we need to find the same amount of molecular orbitals as we have atomic orbitals. So 2 go in, 2 molecular orbitals come out. And let's see our last molecule that we'll discuss here. We use one s and one p orbital now to obtain a total of two degenerate, so two of the same energy, sp hybridized orbitals. This is for a triple bond, right? Something like acetylene here. So we're going to have two pi bonds that form to create this type of overlap here. So we have, to keep things organized, we have the red lobe up here, the blue lobe down here. This is our first unhybridized p orbital in our first pi bond, and then we have another pi bond in the front and along the back. So those two side by side overlaps are what create our second and third, right, of our triple bond here, second and third bond. The sigma bond is created by the hybridized orbital, specifically the sp hybrid orbital with a triple bond, and with this compound here, acetylene. So some things to remember in summation. This slide is good to reference. The sigma bond is stronger, and pi bonds are weaker, takes less energy to break them. And as far as length is involved, an sp3 sigma bond, hybridized sp3 hybridized sigma bonds would be longer than an sp, right? The shorter, right? The more s character, the shorter they will be. So I didn't comment on this, but this one's 50-50, right? That's easy to see. Out of two different orbitals involved, it's one s and one p. So the more s character, the shorter they're going to be. So again, this one would be longer up here. They give us that in summation here. So our sp3 are the longest. You might want to remember this for your first exam, the length and hybridization correlation. And last but not least here, this slide gives you a graphic representation of the molecules here. So we have an overlap of a sp3 hybridized orbital in ethane through sp hybridized over here with acetylene and everything in between. And then we have the corresponding lengths. If you forget how they correlate, sp is the shortest, sp3 is the longest, and also the energy involved in these single, double, and triple bonds, right? The hybridized energy specifically. So that is everything for this section, and we'll continue with section 1.11 with the next video.